Okay, the last thing was we were studying catalysts. Transition metals were substances that formed ions that had incomplete d subshells. We discussed that they were having a high charge density because they've got more protons, so they're smaller in size. They act as good catalysts. Why? Because they're kind of in the middle. They don't like to gain electrons. They don't like to lose electrons. So they can kind of do both things. Okay? Unlike the elements that are on the right side or on the left side. So we discussed all of this. We discussed their behavior as catalysts. Basically, we discussed. We did the catalyst part, both homogeneous and heterogeneous catalysts. That was over. Now, the next thing that we're going to talk about is we're going to talk about the d subshells. So what are d subshells, and how are d orbitals different from the other ones, the s and the p? So starting off with d subshells. Now that's a characteristic property of any transition metal that they've got d subshells. I mean, they have d subshells that are not yet full, not completely full. So d subshells, or just a subshell. Now the d subshell consists of 5 d orbital. I mean, I'll just quickly first do electronic configuration of iron, which is 1s2, 2s2, 2p6, 3s2, 3p6. And then you had 4s2 getting filled up, and then it was 3d, which had 6 electrons. So the last electron in a d block element goes into a d subshell, and when these atoms or ions, they form when transition metals, they form ions, for example Fe3+, then the outermost is usually just the d. I mean, instead of having 6 electrons, it's going to have 5 electrons. So when you talk about transition metal ions, which they are, I mean, when they form compounds, they're mostly ions. The outermost subshell is the d subshell. That is the one that's involved in a lot of things. So the idea about a d subshell is that there are 5. Any d subshell consists of 5 d orbitals. You've got the dxy, you've got the dxc, you got the dyz, and you have the dx square minus y square, and then you have another one which is the dz square. So these are your degenerate orbitals. So that's a d subshell. Consisting of 5 d orbitals. A maximum of 10 electrons can be accommodated in the d subshell. So each of the orbitals, you can keep 2 electrons. So 10 electrons maximum. Now, a d subshell is basically a group of degenerate orbitals, which means that they are all at the same energy level, which means that they're identical. There's no difference between them. So it's a group of degenerate orbitals. Which basically means the word degenerate over here means that they're identical. They have absolutely no difference. Just a second, the board is stuck. So it's a group of degenerate orbitals, which means that they have exactly the same energy level. No difference between them. So there are 5 sets of orbitals. The only difference between them is the orientation. So just like a p subshell, instead of drawing that, I've just copied it from somewhere. So just like the p subshell, if you have a look at the p subshell, you'll notice, where's the p subshell? Just a second. So where is the p subshell? So I'll just copy this one. So I'll first talk about the p subshell. Now here's an image of a p subshell. Now the only difference between them is that the orientation is different. The electron in the first one, this is px. Okay, we're already familiar with the p orbital, p subshell. So this one is the px subshell. This one, orbital. This one is the py, and this one is the pz. So the electron over here is lying on the x-axis. Over here, the electron is lying on the y-axis. Over here, the electron is lying on the z-axis. Its negative charge is lying on the z-axis. So the only difference is that all three are identical, exactly the same energy level, except that the orientation is different. So if I were to draw them together, then it would kind of look. So if I were to draw them together, then it would kind of look like this, that there would be an electron that would be existing on the x-axis. So the negative charge would be spread around the x-axis. Then there's going to be an electron that would be existing on the y-axis. So the electron would be residing or existing on the y-axis. The negative charge would be on the y-axis, and then there would be a z-axis, and there would be one electron on the z-axis, or two electrons. An orbital can have a maximum of 2 electrons. So the negative charge would be spread around the z-axis. Okay, so think of the electron as a negative charge. So the negative charge would be all over the place on the x-axis, 2 electrons on the y-axis. So this is what a p subshell looks like. Now a D subshell is no different. I mean, it's not that different. It's almost the same. Together, this is called a P subshell. So the D is kind of exactly the same, except that the negative charge is spread over 4 lobes. So a typical D subshell. So the first thing is I'm going to draw a typical D subshell. D orbital, basically. So a typical D orbital kind of looks like this. Let's say there are 2 axes. So the negative charge would be the nucleus is right in the center. The negative charge of the electron would be lying on the axis, above, below, to the left side, and to the right side. So if there's an electron in this particular D orbital, the negative charge of that electron can be felt in all these areas over here. There would be 0 probability of finding the electron in the spaces between them. So very little chance of finding the electron or finding the negative charge over here. No negative charge appearing in the middle spaces over here, but there would be a very strong negative charge that would exist on these 2 axes. So that is one typical D orbital. So just like a p orbital, which had just 2 lobes, the D has actually 4 lobes. It's a clover leaf shaped orbital, most of them, and they've got 4 lobes. And there would be different types of D orbitals. Most of the time, the only difference is the orientation. Just like the P, the P could exist on the x-axis or the y-axis or the z-axis. The electrons in the D orbital can exist in different planes. Okay, is this clear? Bhaskar, is this clear? Sam, is this clear?
Yes, sir. Yes, sir.
What a D orbital is. So I'll just copy the shape of a typical D subshell. So this one kind of shows the orientation as well. So okay, this one is even better, I think. So if just a second. So we'll copy this one. So this one. So you got these 4 lobes where the electron could exist. Now, these are just names of the orbitals or the name of the orientation. I mean, dzx means that the electron can be found between the z and the x-axis. I mean, this doesn't really clearly show this. Does this? Just a second. Okay, let's take this picture 1 second. Okay, I'll just. So let's take this one. Okay, the axes are labeled as well. Now this one, 4 lobes. The electron could exist in.
Sir, will these 4 lobes contain 2 electrons?
Maximum is 2 electrons. So I mean, if there
Okay.
two electrons in the dyz, what that yz indicates is, I mean, you have to understand what yz means. Yz means that the electron, I mean, the typical shape, the electron exists between the y and the z axis. It's not on the x axis. So it's in a particular plane. I mean, they've drawn the plane as well that's lying. So it's basically the yz plane. So the electron and the negative charge of those 2 electrons, maximum 2 electrons, that negative charge could be felt in these lobes over here. You can remember it's not lying on the x-axis. The x-axis is not included. Similarly over here, if it's dxz, that means the electron lies in the xz plane. And the electron is lying between the x and the z axis. So you can see you have the z axis, you have the x axis. So the electron probability is maximum between the x and the z axis. Okay, so it's not lying on the y axis. Similarly, you have the dxy. Now the electron is lying in the xy plane, and it's lying between the x and y axis. So the electron or the negative charge of the electron can be found between these in these areas, not on the x and y axis, between the x and y axis. Then you have a fourth one. You've got a dx square minus y square. What that means is that the electron is lying exactly on the x and y axis. So the electron is lying, the negative charge is on the x-axis, on the y-axis. So maximum 2 electrons in this area. And the last one, remember the nucleus, all the spaces around the nucleus are now full of electrons. I mean, you have electrons lying between the z and axis, z and y axis. You have electrons lying between the z and x axis. You've got electrons that are lying between the x and y axis. You've got electrons that are lying on the x and y axis. Now, the only place left is the z axis. That's the only one. So the 5th orbital, the only empty space available is this one. So this one has a different shape compared to all the other ones, because after all those spaces are full of electrons, the only space available is to keep electrons on the z-axis. It's kind of like a p orbital, but it's got a donut-shaped ring around it. There's a region of very high probability around the nucleus in this donut-shaped area around the nucleus. But otherwise, it kind of looks like a p orbital. So that's a dz square, 2 electrons in this one. So you've got 4 typical d orbitals and one which has a different shape. So remember this different shape as well. So you'll be asked to sketch any one of them. They'll give you the axis, or maybe just 2 of the axes. So you can just, you should know that dxy, what does dxy indicate? If they ask you to draw dxy, and if they have just given you, they wouldn't expect you to draw 3-dimensional diagrams. At best, what they can, what you'll get is something like this, that they might give you just 2 axes, and they'll not the third axis, and they'll just ask you to draw dxz. So you just label one of them as x, the other one as z, and the electron probability would be maximum between the axes. If they had asked for a dx square minus y square, then you could have drawn. What you could have done was draw the x and y axis, and the electron would be on the x and the y axis. The negative charge would be found on the X and Y axis. So for you, most of the questions would be 2-dimensional, not 3-dimensional. Okay. So is this clear?
Yes, sir.
So now, the other thing is, look at these two diagrams. This will come in handy later on. What you should realize is that you've got two sets of d orbitals. There's a difference between these two. Okay, so I'm going to divide these into two sets. Although all 5 are identical, they have exactly the same energy levels. But you should be able to figure out this, because this is going to come in handy later on, that the first set of orbitals, the electron probability or the electron probability is between the axes. In all 3, the electron can be found between the axes. And then you have these last 2. Over here, the electron probability is on the axis. I mean, the maximum probability of finding the electron on the negative charge is, the negative charge is existing on the axis. So lies on the axis. Okay, this is going to come in handy when we study the colors of transition metal ions. So that's one thing. You've figured out that a D Subshell. That is what it looks like. And the next thing that we're going to study is going to be, okay, let me just quickly, one second. I think. So we're going to study complexes, and let me just see if we have missed anything. So this one, 28.1, they form colored compounds. We did discuss this earlier. Behaviors catalysts, we're done with that. Complex science, TK. So it's all about complex science now. And all about complex science. So we're going to start studying complex ions now. And we'll start with the first one. TK. So what's a complex ion? Metals, not just transition metals, pretty much all metals, they form complex ions. Or transition metal complexes. Now, complex ions, when you talk about complex ions, think of copper sulfate dissolving. Let's start with copper sulfate. They've got 2 favorite transition metals. One of them is copper, and the other one is, copper was their favorite even in O-levels. The other one is now, it's in recent years, they have a second favorite, and that's cobalt. So we'll start with copper sulfate. We know that copper sulfate is very, very soluble. So copper sulfate dissolves. It dissolves and it dissociates and turns into copper 2 plus, aqueous, and SO4 2 minus, 2 minus aqueous. So we've always studied this, that a transition metal or any metal compound that is soluble, it dissociates in water and turns into aqueous ions. So what happens is, okay, previously you had a copper ion and you had a sulfate ion, and they were all tightly held together. And there were lots of them. They were forming an ionic lattice. So I'll just copy this and draw the ionic lattice. So lots and lots of them were tightly held together in an ionic lattice. They had positive ions and they had negative ions. The sulfate ion is the negative one. So you had copper 2 plus, you had SO4 2 minus, 2 plus, and SO4 2 minus, and 2. This one would be 2 minus. This one would be 2 plus. 2 minus, 2 plus. So anyways, that is what a typical ionic lattice looks like. Copper 2 plus, SO4 2 minus. There would be strong attraction. So they form a crystal. Copper sulfate has this crystal. It's a dark blue crystal. So it's a dark blue crystal, which you must have seen. I mean, this is what copper sulfate looks like. I mean, it's better to. So copper sulfate crystals are these blue crystals. Should have written just blue, not dark blue. And when you mix it in water, it forms copper sulfate aqueous, which is this blue solution. So it turns into this blue solution, or sometimes a dark blue solution, depending on the concentration of copper sulfate. So this is what we are doing. We've got these dark blue crystals, or just blue crystals. Forget the dark word. Okay, so I've got these blue crystals, and they're turning into this blue solution. So what's happening is they're turning into a blue solution of copper sulfate aqueous. Now in this we're going to study why they have colors in the first place. But the first thing is, let's discuss what is going to happen when they dissolve, they dissociate. That means all the ions, they scatter in water. The 2 plus and the 2 minus, all of them, they all are swimming around separately. So you've got 2 plus SO4 2 minus, and 2 plus and SO4 2 minus. So they're all randomly just swimming around in water. You can remember they're in aqueous state. Now it's not that when they get dissociated, it's not that copper 2 plus. Let's focus on this one. You got copper 2 plus, and remember it's surrounded by water molecules. So let's focus on this copper 2 plus now. Now this particular copper 2 plus, let me rewrite this. Remember, it's surrounded by water molecules, and it's surrounded by water molecules, and water molecules have lone pairs. So what happens is, so let me, so what goes on is that these water molecules, they start coming in, and they start getting attracted to this copper 2 plus. Remember, it's surrounded by water molecules. Water molecules are highly polar molecules. They've got lone pairs which have a very strong negative charge. The hydrogen has a positive charge. I mean, it's a polar molecule. But focus on the lone pairs. The lone pairs are going to be attracted to they're going to be very strongly attracted to this copper 2 plus, and they're going to be attracted from all sides. Okay, they'll be trying to approach this particular copper 2 plus ion from all sides. All the lone pairs are going to be attracted to this copper 2 plus. So you've got and here's another one. And here's the last one. And these would be dative bonds. It's a dative bond that would be formed, a dative bond or a coordinate bond. Now a coordinate bond is formed. What's a coordinate bond? Because it's a bond where one atom provides both the electrons. The other atom is not contributing anything. So you've got this copper 2 plus over here, which is absolutely not doing anything. It's just an ion with very high charge density. The 2 plus is the charge is concentrated over a very small ion, and that 2 plus charge is attracting all the water molecules that are around it, and their lone pairs specifically. So the lone pairs are getting attracted to the copper 2 plus. So both electrons, the reason it's a dative bond is both electrons in the bond belong to oxygens, or are lone pairs on oxygen. So yahan tak, is this clear?
Yes, sir.
Yes, sir.
So both lone pairs are basically in the bond are lone pairs on oxygen. So it's a dative bond. So it's so next time when you see copper 2 plus aqueous, it's not just a copper 2 plus that's just randomly floating around in water that has broken away from the lattice. It's not just that. It's a copper 2 plus that is stuck between water molecules because the positive charge has attracted all the lone pairs from all the water molecules surrounding it. Think of this as a three-dimensional XYZ axis, and from all sides, water molecules are approaching it. And this is called a complex. So this entire thing is now one thing actually. So the thing that you call copper 2 plus aqueous is not actually just copper 2 plus aqueous. It's copper 2 plus stuck with 6 water molecules. So let me put a bracket around this. And this entire thing will have a charge of 2 plus. So this entire thing, remember, this entire thing has a charge that is of 2 plus. Why does it have a 2 plus? Because you've got one species that has a +2 charge, the other ones are all neutral. So I mean, this +2 charge is going to disappear because it's going to get electrons from everywhere. But if you add up the charges of all the species that are involved, the waters are neutral, which means that they have the same number of electrons and protons, so they're neutral. Copper is the one that's electron deficient, but if you combine them together, +2, 0 charge, everything else is 0 charge. So the overall thing will have a charge of +2. So which is why you're not going to write +2 on this copper, because this copper, after getting electrons from all the other water molecules, the +2 would not just be concentrated on the copper only. It would be the electron deficiency would appear on the entire thing. The entire thing would be +2. The total charge on the entire thing would be +2. So just remember this. Okay, whenever you have two things getting attracted to each other, I mean, the charge is now the overall charge. It's not going to be concentrated on one of the atoms or the other one. It's going to be on the entire thing now. Okay? You be clear? Is this clear?
Clear.
Acha, you've got, how do you write this? The way you write this is, I mean, this is how you draw it. The way you write this is you call this Cu with 6 water molecules. And the entire thing has a charge of +2. That's how you write complexes. Complexes are written usually in square brackets. And this is, although you don't have to be very specific about naming complexes, this one is hexa, aqua, copper, 2 complex. So the naming is kind of simple. It's hexa means 6. Aqua means it's surrounded by water molecules. You got a copper 2 ion stuck in the middle, and that's your hexa aqua copper 2 complex. That's it. Otherwise, you don't really have to be very concerned about naming. So that's one of your complexes, and remember, it's this complex that has a blue color. So
Sir, will every complex ion have 6 water molecules with it?
I said, now that's a good question. Now the thing is, why does it have 6 water molecules? So the thing is, that's known as the coordination number. Let's talk about the coordination number. Coordination number is, it's the number of coordinate bonds that it's going to form. Okay, just 1 second. Let me first also state that this species is known as a ligand. Okay, this one is known as a ligand. So you'll be asked about the definition of ligands. Ligands are species that have lone pairs. That have lone pairs and can form coordinate bonds. So they can form coordinate bonds with a central metal cation to form a complex. They'll ask you about this definition as well, to form a complex ion. So remember what a ligand is. We'll be using the word ligand very often now. Another thing is, I did not write the definition of a, sorry, band ho gaya, just a second. Where did the port go? Just 1 second. Okay. So also, we have to write the definition of what a complex ion is. So it's kind of the same thing. It's kind of the same definition, that it's an ion that is formed when a central metal ion when a central metal cation forms coordinate bonds with a ligand. अच्छा ये सारे. I said, now coming back to the question. So how do you figure out, I mean, why is it making six dative bonds?
Sir, is it just for like transition metals, or can sulfate ion do it too? Because it has a charge of 2 minus. It can attract hydrogen in water.
Exactly.
That
I mean,
form
it can do that. Okay, it can obviously do that. But here's the thing, that it won't form a complex like for example, you've got a sulfate ion, right? Sulfate ion is this thing. Okay, you do have a sulfate ion. It's it's SO4. I said it's SO4 2 minus. So there's -1 charge, it's got lone pairs here, and there's another lone pair which is over here. Because that's a sulfate ion. So it can obviously form or attract water molecules. So here's a water molecule, and that water molecule is going to be attracted to it, right? Because the water molecule is polar. The lone pairs are negatively charged. The H is positively charged. So it's going to attract the water molecule, right? The only thing is that it's going to do something similar, but it won't form dative bonds, because for a dative bond, you need an element that has a completely empty orbital or empty shell, right? You get my point? Hydrogen already has 2 electrons coming from oxygen. Bhaskar, is this clear?
Oh, yes, clear.
Okay. So there's going to be attraction. There might be a dative bond formed if this hydrogen decides to let go of these electrons and the water ionizes, but water doesn't really ionize a lot. So there is a chance that the dative bond could be formed, but for the dative bond to form, the H must have it must have empty shells in the first place. Why is copper able to do that? The reason copper is able to do that is because it's a copper 2+ ion. It's already lost its outer shell. So the outer shell is completely empty. It's got a lot of empty orbitals. Okay, agar aap copper 2+ ki, if you write the electronic configuration of this thing, so copper 2+, the outer electronic configuration, forget all the other ones. We can just write argon, and then after that, you have 4s2, and you have 3D. So copper is that special case. So it was actually 3D10 and 4s1. Okay, so when copper ions are formed, copper 2+, this is gone, so there's 0 electrons here. And the D is also has now 9 electrons. So the outer shell is completely empty. The outer shell has 4p subshell. That's also completely empty. It has the 4d subshell. So it's got, the outer shell is completely empty, which is why it can form dative bonds. If the copper 2+ ions attracts all these lone pairs, which it will because it's got a 2+ charge, the outer shell is completely empty. So remember, it's the outer empty shell that is involved in dative bonding. So all the lone pairs in the outer shell, they're getting attracted in the outer shell. The inner shell is almost full, so it doesn't have any space. The 3D is almost completely full. Okay, is this clear?
Yes, sir.
So now, just quickly, coordination number, I'll just end it over here. This is the first one that we drew. Okay, we have to. So coordination number, I'll just talk about that. That is the number of coordinate bonds in a complex. And it could be any number. It's not a fixed number. It's a number of coordinate bonds in a particular complex. So it could be 2. Over here it's 6 because there are 6 coordinate bonds. So it depends on a number of factors. It depends on the strength of attraction. Like if the attraction is really strong, a lot of water molecules are going to get attracted to it, right? So it depends on how strongly the positive ion in the middle is attracting it. That's one of the factors. Then it depends on the size of the ligand as well. If the ligand is very big in size, so you can't fit so many ligands around it. So it depends on a number of factors. It depends on the size of the ligand, depends on how strongly is the metal ion attracting those ligands. TK, is this also clear?
Yes, sir.
So we'll continue with this, TK, in the next class now. TK, it's and we'll discuss ligand exchange. We'll talk about colors of these. This is the first one. Remember, copper is their favorite, so this is the first one, which you already know. So we'll do the other ones. What happens when you add ammonia to it? What happens when you add OH ions to it? What happens when you add Cl -1 to it? So we'll talk all about that in the next class then, okay? So let's continue tomorrow then. Okay, everyone.
Allah.
Take care, Allah Hafiz.